Welcome back, everyone, to our weekly science news. Today we'll talk about a bubble of galaxies, a climate scientist who made his own paper worse, double magic oxygen, a chemical reaction slowed down 100 billion times, Maxwell's demon in biology, intelligent life on Earth, the launch of a new X-ray space mission, drone racing, and of course, the telephone will ring. Astronomers in Hawaii have spotted a massive bubble of galaxies. It's approximately 820 million light-years from Earth and 1 billion light-years wide. They called it Ho'olailana, Hawaiian for murmurs of awakening, because they believe it's a direct remnant of murmurs from the time our universe awoke. The astronomers weren't specifically looking for this galactic bubble, but at that size it was kind of hard to miss. That it's a bubble means the galaxies seem to be more likely to be located on a giant sphere. This observation fits neatly with our current model for the early universe, which you probably know has it that the early universe was filled with hot plasma, which then rapidly expanded. According to this model, there were density waves in this hot plasma. They're kind of like ripples in a pond, but in 3 dimensions. They are known as baryon acoustic oscillations. Acoustic because they're like sound waves, and baryons are a type of subatomic particles that includes neutrons and protons, the constituents of atomic nuclei. When the universe expands, the plasma cools and begins to clump, and then it forms stars and galaxies. In the places where the plasma density was higher, there'll later be more galaxies. This should give rise to bubble-like structures, exactly like what they observed. You see, it's not just kids who like making bubbles. The young universe was like that too, though with a bubble of 1 billion light-years in size, maybe somewhat of an overachiever. The bubble is like a megastructure of megastructures and contains previously known giant conglomerates of matter like the Coma cluster, the Hercules cluster, and the Sloan Great Wall. This bubble is so big it's hard to wrap your head around it, unless possibly your head is 1 billion light-years wide, in which case I think you could do better things with it than watching YouTube. The most depressing story of the week is a climate scientist who single-handedly damaged the reputation of his entire discipline. Here's what happened. The climate scientist Patrick Brown recently published a paper about extreme wildfires and their link to climate change in the journal Nature. Now that the paper's live, he explained on X, formerly known as Twitter, that while his paper considered climate change as one driver of wildfire risk, it did not properly account for other factors, such as changes in land use, vegetation, and human behavior. And he did this deliberately because he believed it'd improve his chances to get published. He claims that there is a formula to getting published in high-impact journals that requires focusing on the impact of only one variable. It's not like he falsified any data, but he left out relevant context that he full well knew about. Brown defended his action by saying that while considering other factors would have made for a more realistic and useful analysis, he didn't want to muddy the waters of an otherwise clean story. However, the peer review file for Brown's paper is public, and even the reviewers argued against him. Editors from Nature have denied that leaving out relevant variables reduces the chances of getting published. The episode is fuel to the fire of climate change deniers. Who needs enemies with friends like this? Hello. Hi, Rishi. Iceland reintroduces whaling? Oh well. Oh, sure you can do it too. Just tell them it's an experiment looking for dark matter because the whales have been eating up the stuff. Oh, don't worry. Some physicist will come up with a theory for it. You're welcome. A group of experimentalists at the Japanese Riken facility has for the first time managed to produce a heavy isotope of the oxygen nucleus and found a few surprises. The oxygen in the air around us is oxygen-16. It has 8 protons and 8 neutrons in the atomic core and is stable. Atomic nuclei are subject to quantum mechanics and they have shells and excitations just like the electrons around them. And like the electrons around the nucleus itself has shells that can be more or less full. If you remember, the structure of the periodic table comes from filling up the electron shells. How full the electron shells are determines much of the chemical properties of the elements. Noble gases, for example, have their electron shells full. That's helium, neon, argon, and so on. Since the shells are full, they are slow to react. It's why they're called noble. Noble people don't explode. The same is the case for nuclei. Some are more, others less explosive, so to speak. When it comes to atomic nuclei, the full shells are called magic numbers. But since atomic nuclei have 2 different constituents, protons and neutrons, there are 2 numbers. A nucleus which has a magic number of both neutrons and protons is called doubly magic. The common oxygen-16, is doubly magic and it's stable. That a nucleus is doubly magic doesn't necessarily mean it's stable, though. It's more complicated than that. It should, however, at least be strongly bound and hold together reasonably well. After oxygen-16, you expect the next doubly magic oxygen to be oxygen-28, that has 8 protons and 20 neutrons. It's difficult to produce nuclei with that many neutrons. And not only do you need to produce them, you then also need to measure them. But that's what they did in this new experiment. The researchers started by firing calcium-48 at a beryllium target. This results in a lot of lighter atoms, including fluorine-29. They isolated out the fluorine and then dumped that into liquid hydrogen to remove one of the protons. This process generates the oxygen-28. But contrary to expectations, the oxygen-28 turned out to not be doubly magic. The oxygen-28 decayed readily by spitting out 4 neutrons, leaving behind oxygen-24. This is really interesting because clearly there is something about nuclear structure which we don't fully understand. By the way, don't do this at home. Free neutrons are really not healthy. An international group of physicists and chemists has simulated an essential property of chemical reactions. This allowed them to look at the process 100 billion times slower than it occurs in nature and confirmed an essential prediction of quantum chemistry. Chemistry is all about electron energy levels and how the electron wave functions reshape when 2 atoms get close to each other. One particularly essential feature of wave functions is that, well, they're waves, so they can interfere. In particular, they can interfere with themselves. This can lead to very interesting effects if you have a particle whose wave function goes around an obstacle on both sides. Because then what happens on the other side of the obstacle depends on how the wave functions overlap on the other side. They might cancel out or they might add up. This self-interference around an obstacle is a really famous quantum effect, and it's believed to play a role in chemical reactions, such as those contributing to photosynthesis. Problem is, in an actual chemical reaction, this all happens in a matter of femtoseconds. A femtosecond is 10 to the minus 15 seconds, and to give you some context, that's the approximate duration of summer in the UK. In the new experiment, they simulated this process with an ion trap. In such a trap, a charged atom is held in an electromagnetic field. In this case, they did this with a configuration of 4 lasers. These electromagnetic fields generate an energy potential around one axis. The wave function of the ion can't go through this axis, so it goes around and then wobbles back. The observations agree with theoretical predictions amazingly well. This is an example of a direct quantum simulation that needs no quantum computer. Okay, so you might say, but if it agrees with prediction, that's kind of boring. Yeah, but down the line, this could become a useful method to better understand the quantum effects in chemical reactions. I wish to apologize to all chemists in the audience, but this is more proof that chemistry is really just applied quantum mechanics. A group of biologists in Switzerland have found a Maxwell demon in cells. Maxwell's demon is a thought experiment for beating the second law of thermodynamics. That's the one which says that entropy cannot decrease. The thought experiment goes like this. If you have two boxes of gas at different temperatures and combine them, then the second law says the gases will mix and reach equilibrium at a temperature somewhere in the middle. In that process, entropy increases. Maxwell said, let's suppose we enter a wall to separate the boxes again, and we add a little person, that's the demon, which lets fast gas atoms through to the right and keeps slow ones on the left. Then that'd decrease entropy and shouldn't be possible. That confused people greatly at the time, but we now understand that this only works if the demon itself has information about the system which requires low entropy. And the entropy of the demon increases while that of the gas decreases, so the second law remains valid. Still, this has been a very interesting thought experiment because it's led to some ideas for how one can convert information to low entropy. The biologists now found that nature was well ahead of Maxwell. They say that there are certain proteins, known as ATP-binding cassette transporters, ABC for short, that work pretty much the same way. These proteins control the movement of molecules and help cells regulate energy flow, just like tiny Maxwell's demons. Of course, they don't violate the second law either. They use energy from the ATP molecules, which is a low entropy reservoir. So physics wins again. Hello? Mr. President. A study has found that seafood tastes better by the seaside. Well, that's interesting. Yes, you're entirely correct. This must mean that junk food tastes better near the rubbish bin. You're welcome. Always at your service. NASA, together with the Japan Aerospace Exploration Agency and the European Space Agency, have finally launched their shared X-ray imaging and spectroscopy mission, XRISM. Now that it's in orbit, it can get to work capturing the dynamics between galaxy clusters, helping us understand the chemical makeup of the universe and measuring the way black holes affect star formation. The X-ray imaging and spectroscopy mission contains two main instruments. One, called X-TEND, consists of 4 detector arrays that pick up on ultraviolet, visible and near-infrared light. The other, called Resolve, is an X-ray calorimeter. When photons hit this detector, they'll warm it up, changing the conductive properties of the instrument, from which the energy of the photons can be inferred. Resolve requires helium to stay cool enough to operate, and because the satellite can only hold enough helium for 3 years, that's about how long we can expect to obtain data from this mission. So the universe is getting an X-ray. Let's hope nothing's broken. Astrophysicists say that the James Webb Space Telescope has found that there's intelligent life on Earth. Whew, that's some relief. In a new preprint that just appeared on the archive, a group of astrophysicists shows that if the Webb telescope were to look at Earth, it could confirm both the potential for and the presence of intelligent life. They arrive at this conclusion by looking at a bunch of molecules in the atmosphere that the telescope can detect. This includes water, carbon dioxide, nitrogen and methane, but also more complex substances like CFCs. They say that these not only make life possible, but they also imply the presence of technologies that might be created by intelligent civilizations. Combined with contextual data like temperature, pressure, altitude, and so on, the presence of these gases signal that life forms like ours might be near. They conclude that the Webb telescope would be able to confirm the presence of intelligent life on Earth with 88% accuracy. This study is proof that the Webb telescope isn't just for taking pretty pictures of the cosmos. Indeed, the telescope's potential is much wider in scope and might even help us locate those aliens American officials have been blabbing on about. Engineers at Intel and the University of Zurich have used artificial intelligence to build a super-fast, self-flying drone. It's so good at finding the optimal routes and making quick turns that it's capable of beating even the most experienced human drone racers. The drone is based on an AI system called Swift. It collects data through a camera and an integrated inertial measurement unit, which monitors the drone's environment and acceleration. This data feeds into Swift's deep neural network. It works in real time and decides the best route forward and the most efficient maneuvers to make. The system beat 3 of the world's best human drone racers in multiple 100 km/h races. But speed isn't everything. Intel and the University of Zurich also found that human drone operators were more adaptable than Swift, meaning they were able to handle changing conditions and unpredictable challenges more easily. If there was too much light in the room, for example, Swift's lack of adaptability slowed it down. Human racers were also better at adjusting their flight strategies to reduce their odds of crashing. But if all goes well, soon enough we'll all be completely unnecessary and can leave the world to self-flying intelligent drones. Thanks for listening. We'll be back next week.